Well, let me go ahead and get started here. Today, our topic is healthcare economics, looking at cost effectiveness alongside clinical trials. So the first thing that I want to go over in quite a bit of detail is patient level cost effectiveness analysis. And that patient level means that we have costs for individual patients, obviously. So we'll look at estimating cost and then estimating effectiveness, look at cost effectiveness analysis and the cost effectiveness plane, and then sensitivity analyses. And then I'll end up talking about doing this same sort of thing, except we in this situation where we don't have patient level data, and we'll do Markov modeling. So cost effectiveness basically is the is an analysis where we want to determine whether some particular therapy or treatment or medication or device or whatever improves health more than the standard of care or placebo or another treatment. And usually the therapy that we're interested in or the pharmaceutical that we're interested in comes with a higher cost than the previous treatment. And our basic question is going to be, how much is someone, an individual or society, insurance company, willing to pay for the improvement? And so we have the concept of willingness to pay, and how much we're willing to pay for an improvement in health. So the patient level data that we need for a cost effectiveness study is obviously the outcome from the study, which typically is survival or life years gained. In other words, how longer was the survival time for the treatment of interest than the placebo or the standard of care. And usually, in fact, really most of the time, you'll see this expressed in what we call quality adjusted life years, or QALYs. And basically the QALY is calculated by multiplying the survival by a utility, which is a measure of health status that's scaled from 0 to 1, with 0 being death and 1 being perfect health. And then of course, we're going to need the cost of treatments, which is going to involve procedures, physician costs, hospital costs, and obviously medication costs. So how do we estimate patient level costs? Well, you can get them in different ways. No way is particularly perfect. UB04, which used to be another name for that, but is basically like a hospital charge sheet, but that's really difficult to get a hold of. We can look at different reimbursement schedules. We can find costs for what's called a DRG, a diagnosis related group, or in Canada, the same thing is called a case mix group. We can get Medicare or Medicaid costs, although that's not easy to do either. And then for medications, there's different sources for looking at medications. A common one used is the Red Book or wholesale acquisition costs. So obviously these are not absolute costs in a sense that they will vary, and we'll look at that later on in the discussion. So what are we going to cost? Well, obviously we're going to cost the primary events. For example, if we're doing a cardiovascular study, cardiovascular death, myocardial infarction, stroke, heart failure, costing the events. And then another cost might be serious adverse events. So maybe bleeding is a serious adverse event that we're going to need to cost. We might need to, depending on the particular studies, cost subsequent hospitalizations. So for example, if we're looking at heart failure, do we have subsequent hospitalizations for heart failure that we need to include in the costs? And then physician costs, which are separate from hospital costs. Usually, you probably have experienced this, and if you've gotten a hospital bill and then weeks or even months later you get another bill from the physician, but those are not easy to cost either. In fact, what we do is we take a percentage of the hospital cost. Then maybe there's going to be follow-up costs. Does the patient need rehab? And then, of course, a really important one, particularly for pharmaceutical studies, is the cost of medications. And even if that would include medications that are being normally taken by the patients, like statins, for example. And then another cost issue is lost wages, but in the past that's not really been looked at too much because it's very difficult to estimate. Although more recently, some people have started to look at that, so we might see more of that for cost effectiveness studies in the future. So here's an example from actually a really old study of looking at clopidogrel versus placebo. And this is an example of costing by DRG, diagnosis related group. And so you have a number that you look up for the particular diagnosis that you're interested in, or the particular event that you're interested in, or procedure. And in this case, what we did is we looked at the number of hospitalizations and then what those would cost. We had two different costs, a MedStat cost, which is a database of cost, and then Medicare costs, where we would use the Medicare cost for patients 65 or older. And here's a more recent table of example of cost. These are 2018 costs, looking at just two examples. Here is a fatal cardiovascular event by age, and then a non-fatal myocardial infarction, again by age. And so what we use in the cost is the mean cost. I'll talk about that in a little bit. Usually we present a table like this where we have the mean cost that we've obtained from some particular source, the standard deviation that we have for that cost, the minimum, maximum. And then out in the right-hand column, you can see the distribution. And so this is something that's presented as the costs and the utilities that we find. What is the distribution of these? And for costs, you'll invariably see a gamma distribution. And what do we mean by that? Well, if you make a histogram of any cost of anything, it's basically going to look like this. And so you have a right skewed distribution. And so we're going to model this distribution as a gamma distribution. And you can see that most of the costs are on the left-hand side of the graph, higher cost out in the right-hand side of the graph. That's why we call it right skewed. And you say, well, why don't we either just disregard the high costs as outliers, but in doing cost-effective analysis, you can't do that. As long as it's a legitimate cost, you have to include it in there. And that's why we use mean costs, not median costs. And another argument might be, well, what if you take a logarithmic transformation of this? Well, even if you do that, you get the same histogram, the same distribution. So we're going to model cost as a gamma distribution. Utilities that we use to get quality adjusted life years. This is a measure of patient quality of life. And as I mentioned, it's scaled between 0 and 1. And the best of all worlds is to have patient-reported utilities. That is, they rate their own health. And this would be obtained during the trial with some particular published instrument. The most popular one being what's called the EQ5D, which is a 5-item instrument where patients rate their own health, and it's then scaled from 0 to 1. If we don't have patient-reported utilities, then we'll have to estimate them from a similar sample, which usually is you can do really only by age and sex. So if we don't have actual patient-reported outcomes, then we'll have to find some source to estimate what the utility might be. And so here's an example of utility values from a recent study that we did. And so the first column there, chronic utility. So if a patient had no history of cardiovascular disease, then you get a value of 1. If they have a history of angina, then it's 0.9, or a history of MI, it's 0.96, and so on. So this is a starting point, and there can be more of these. In this particular study here, it was cardiovascular histories. So this is our starting point. So as I mentioned, if they have none, we start out with a value of 1. Then if they experience any of the events of interest during the study, then we have what's called a disutility. So in other words, if they experience one of these events during the study, then there's a subtraction to the value, to the utility that they started out with. And so you can see that this is value between 0 and 1, so we're going to model it as a beta distribution. And of course, you need to have references where where these things came from. So, oops, let me go back here. So we measure trial effectiveness, or the study effectiveness, primarily by looking at survival and calculating the life years gained. In other words, the difference in survival in life years between the treatment and the placebo or the standard of care. And then to get quality adjusted life years, we just multiply the utility that they have times their life years. So obviously, if you have a utility of 1 and your, say for example, your life years is 4.5, like I have an example here, then that's what your life years gained is going to be, is 4.5. On the other hand, if you have had a history of stroke, then we're going to multiply the 4.5 times the value that was in the previous table, 0.88. And so instead of having 4.5 life years gained, we're going to have 3.98, or essentially 4 life years gained. And then if that patient has say a non-fatal stroke during the trial, then we're going to subtract that value, which in the previous table was 0.01 something. So we're going to end up with quality adjusted life years of 3.97 for that particular patient. The primary statistic that we're interested in is what we call the incremental cost effectiveness ratio. And so this is the difference in costs between the two treatment groups divided by the difference, the mean difference of the effectiveness. So we have the mean of cost in treatment A minus the mean of cost in treatment B divided by the mean effectiveness in treatment A minus the mean effectiveness in treatment B. And so this is our statistic that we're going to be interested in calculating. And so what do we mean by cost effective? Well, in the US, it's traditionally the kind of standard for the incremental cost effectiveness ratio, or the ICER, as we call it, has been $50,000. And what does this mean? Well, that means that you're willing to spend $50,000 for, say, for example, one quality adjusted life year gained, or if you're just looking at life years gained, for one life year gained. And so of course, the question is then, this is not obviously an absolute number. It's just a number that's been used for several years. More recently, people have started to use $100,000 or $150,000 because things obviously cost more than they did 70 years ago. And so the question is then, what are we willing to pay? What is our willingness to pay threshold here? And that depends on our perspective. And so there's different perspectives that we can take. Usually we take society's perspective. We can also do cost effectiveness from the insurance company's perspective, or the payer's perspective. So our willingness to pay, again, is a number that's arbitrary, and it will sort of depend on the particular study that we're doing. So how do we analyze the ICER? Well, as we'll see, ICERs might have the same sign and be exactly the same amount, but they would have different meanings depending on the sign. And because we're looking at a ratio of differences in mean cost divided by the differences in mean effectiveness, we need to come up with a sampling distribution. And so it turns out that it's very difficult to, if not impossible, to model this with a theoretical distribution like the normal or the gamma or beta distribution. And so what we're going to do is bootstrap our data to get a sampling distribution. And we're going to bootstrap with replacement. And what that means is that we draw random samples from our data, and we're going to draw as many samples as we have number of patients. We're going to then calculate the ICER, the cost, the difference in cost between our groups and the difference in effectiveness. In bootstrap with replacement, then you replace each observation after it's drawn, and you're putting it back into the pool, so you can see that when you do bootstrap with replacement, it's possible to get the same observations in different bootstrap replicates. But we do this a large number of times, usually 5,000 to 1,000 times, and it results in a distribution of the statistic of interest, primarily the ICER. And then we plot this distribution of 5,000 or 10,000 ICERs in what we call the cost effectiveness plane. And so the cost effectiveness plot here is on the horizontal axis. We have the effectiveness, and so going from left to right, the treatment of interest is more effective. On the vertical axis, we have the cost, and so going from bottom to top, of the plot, it becomes more costly. So we start out by looking at where we divide the cost effectiveness plane into 4 quadrants. So the heavy lines here, these represent 0. So 0 effectiveness and 0 cost, meaning that the difference in costs or the costs are the same. There's no difference. So we start in quadrant 1 here, and this is referred to as the cost effectiveness quadrant. So we have higher cost, but we have more effectiveness. And so this is where we're interested in calculating our ICER to see what that is. Quadrant 2 is actually the quadrant everybody'd like to be in. This is where the effectiveness is greater in your treatment group, but the cost is less. And so if our bootstrap replicants fall into quadrant 2, then we say that the treatment is dominant. That is, we have less cost, but more effectiveness. Quadrant 3 is sort of, I guess, a nondescript quadrant here where we have lower cost, but we also have lower effectiveness. So if they fall in quadrant 3, then the decision is made as well. It's cost less, but is the effectiveness, still worth the cost? And then quadrant 4, where nobody wants to be in their analysis, is where we have higher cost and less effectiveness. And if our bootstrap replicants fall in quadrant 4, then we say that the treatment is dominated. That is, it's more expensive and it's less effective, which is not a good place where you want your study to end up. And so I just give a numerical example here of using the same numbers to show that we can get the same ICER, but depending on the sign, it has different meanings. And so in quadrant one here, the treatment costs $500, the standard of care $200. There's a difference of 0.5 or a 0.3. So this is $1,000. And so it'd be cost effective. That is, it costs more, but it's more effective. And then quadrant 2 would be dominant. We would get a negative ICER, which we actually don't report negative ICERs. And then, for example, in quadrant 4 here, where it's more expensive, but less effective than the standard of care. And so this is an example of a graph that's of how we plot, how we show the cost effectiveness plane with our bootstrap replicates. And so we have the horizontal and vertical axis here to show, find out what quadrant we're in. And so our example here is that most of our bootstrap replicates fall in quadrant 1 in the cost effectiveness quadrant. And the diagonal line here we put in to whatever our willingness to pay figure is. And so in this particular example here, our willingness to pay was $20,000 per life year gained. And so what this means is that everything below our diagonal line here would be cost effective. And so you can see if we put different willingness to pay thresholds in here, the diagonal line is going to be, moved up or down. We then also plot what's called the cost effectiveness susceptibility curve, where we plot on the vertical axis the probability of cost effectiveness, and on the horizontal axis we plot our threshold. That is, and we usually plot it from 0 to like out to 100 or 150 or $200,000. And so an example of this from the last plot, the cost effectiveness plane, our our cost-effective acceptability curve in this case is really good because we see that that the probability here of it being cost-effective, that even at $20,000, the probability of our treatment being cost-effective is 90%. So, and here we have usually the dotted vertical line here represents the $50,000 willingness to pay threshold. So we can see that in this case that our cost effectiveness is in terms of a cost per life year gained is really pretty good. Other things, plots that you might see, this one is kind of a strange looking plot. It has to do with the range of the cost, but you can see that here we have a dominant strategy, or whatever it is we're looking at here, because all of the, or virtually all of the bootstrap replicants fall in quadrant 2. So this means that it costs less and it's more effective. So this would kind of be what we hope, sort of hope for in our cost-effective analysis. This one, you can see that, well, we're not really quite sure that it shows anything because we have kind of an even spread of our bootstrap replicants in all 4 quadrants, although most of them look to be in quadrant 4. So we have whatever our treatment is that we're looking at here, it's looks like it is generally is going to cost more and be less effective. Okay, so then another idea that we need to talk about here is when we do cost-effective analysis is discounting. And this is basically the idea that the value of the treatment diminishes over time. So the quality or the adjusted life years would diminish over time, the costs diminish over time. And by that, I mean, it's like the whole spectrum of the value. I'm not talking about inflation here with cost, but we don't discount anything in the first year. In the second year of our trial, we say if we're discounting at 3%, then we would multiply our costs by 1 divided by 1 plus the cost or the discounting rate squared. And in our third year, then it would be the same value raised to the power of 3, and so on for the 4th, 5th, 6th, however many years our study lasted. And we usually vary this discount from 0 to 3 or 5, or usually 6. Maybe I've seen some go up to 10%, but that's usually people don't discount that high. So I want to then share a study that we did, a cost effectiveness study, show you how this is actually presented when you publish it. And so this is the study looking at the cost effectiveness of icosapent ethyl, or IPE for short, for patients with hyperglycemia that are taking statins. And this was published early, I think, last year, 2022. And so our objective was to estimate the cost effectiveness of IPE compared with standard of care for these high-risk patients. And so the study was a really quite large one. We had some 8,000 patients. I would also mention that this was also a multinational study. And some patients, about 3,000 of the patients came from the US. Other patients were spread around different countries in the world. I think like Europe, the European countries, maybe some Eastern European countries. I don't remember exactly anymore. But we have a statement in here that analyses were performed from a U.S. healthcare perspective. So what we're doing is we're taking everybody, even though they are in different countries, but we're applying the U.S. costs to them. And I'll talk about that a little bit later. And so our intervention was IPE, 4 grams a day, or it was 4 1-gram tablets a day, or placebo. And these patients were followed up for a median of virtually 5 years. And we looked primarily at 2 different costs of the drug. The first one, the least expensive, was $4.16 per day. And we used what's called SSR, Health Net Costs, which includes rebates. Then we used the wholesale acquisition cost, or WAC, or the Red Book cost, which is over twice the SSR cost of $9.28 per day. So basically, with the SSR cost, you're looking at $1 and some per pill. With the WAC cost, we're looking at over $2 a pill. And then, so obviously, what we're going to look at is the cost effectiveness of IPE. And so this is a table that is usually presented. I didn't present the table from the paper because it was vertical, and I just took a part of it here to show you how this is presented. So what we're calling our base case, where we're doing 3% discounting. So our IPE group, it cost $18,000 plus for the drug for IPE. For the standard of care, it was $17,000. So the difference in the mean cost here is $1,500. Then we're looking at quality adjusted life years here. So the quality adjusted life years for IPE was 3.34, and for the standard of care, 3.27. And the difference these is 0.07. So our incremental cost effectiveness ratio here is $22,000 and a little bit more, which is just the 1,500 divided by the 0.07. And then we present here what's the percentages of the bootstrap replicants that are dominant, that are dominated, that are less than $50,000, less than $100,000, and those, how many or what percentage are less than $150,000. So you can see at the $50,000 level, we have 85%, and then at 100,000 up, it's 95% and over. And then we also have, and these are in trial analyses. We do obviously 0% discounting. So this is what the cost is. If you don't do any discounting, we still get an ICER that's 22,000 and some. And then we did a 5% discount, where again, it's about 22,000 some. So what this means is that to gain 1 quality adjusted life year, we're going to have to spend about 22,000 and some dollars. And then this is how our graphs appear in the study. So in top here at the A and B, we have our cost effectiveness plane, along with our willingness to pay threshold of $50,000 in there. And the first one, panel A, is the SSR cost of $4.16 a day. B is the WAC cost, the $9.28 a day. And so you can see the big difference here, that the big driver in cost effectiveness analyses is the cost of whatever the drug is, or whatever the particular treatment is, or the surgery, or whatever the treatment is you're interested in. And then the bottom here in panels C and D are acceptability curves. And so you can see here that for the IPE group, we have our $50,000 threshold. About what we saw is about 85%. And then if we're out to $100,000, it's over 90%. Here you can see that if we're using the higher cost, the $9 a day cost, that the probability of being cost effective isn't very good. And in fact, we're out here at $100,000 and it's still not, the probability is still not at 50%. Then these are what are called tornado diagrams, and these are the sensitivity analyses that we do. And so what we do in this case is we vary different components of the cost or of the effectiveness. And obviously these are the one that we put on top here is the cost, which is going to be the most dramatic. So that's why they're called tornado diagrams, because you got the biggest part of it at the top here. So here, if we vary the cost of IPE from $3 a day to $10 a day, we can see that if it's less than the 416, then we're going to have a smaller ICER. But if it costs more than 416, which is the line here, then obviously the ICER is going to be quite a bit larger. And so if the cost of it is out here at $10 a day, then the ICER is going to be pretty large. And then we do the same thing using the WAC cost, and so we have the same range here, $3 to $10. And so obviously the lower the cost, the better our ICER is going to be. And if it's actually more than $10, it's going to be, the ICER is going to be a lot higher. And then we do the same thing. I'll talk about this at the end. A and B here are in trial sensitivity analyses, and C and D here are what we call lifetime analyses. That is, we extend the analysis beyond the trial period, and I'll talk about that later. And then this is another aspect of sensitivity analysis we do. In this case, we find different costs for IPE. And so in our panel A here, which is our in-trial analysis, we have our SSR cost. We have costs that we got from the VA federal supply cost, which is fairly similar, but a little bit higher. Then our WAC cost of $928, and then some costs that are actually higher than that, and some that are in between. And so what we calculate based on these costs is what would the willingness to pay threshold be? What would be the incremental cost effectiveness ratio given these different costs? And so you can see here that our cost of IPE at the $4.16 a day is like we had $22,000. If it was $4.60 a day, then it'd be probably somewhere around $30,000. The dotted lines here are calculated what it would be at 50, 100, and 150. Although in this case, the $884 per day cost from NADAC was right at the $100,000 ICER. So that's why this is blue and not dotted. And then we do the same thing for the costs over the lifetime. And you can see here that it turns out that at our low cost of $4 and some a day, that it's actually below zero, which means that it's dominant rather than just cost effective. So this is another way of doing sensitivity analyses. Okay, so let me then turn to doing Markov modeling, where we don't have individual patient data, so we have to get estimates of costs, of rates, rates of our event, or whatever else we are going to look at. And essentially, these are typically obtained from previously published literature. And what we're going to do is a simulation study of cost effectiveness and sensitivity analyses. In the same way, we're going to vary the inputs. And then I want to, at the end, talk about probabilistic sensitivity analysis, which is essentially a Bayesian analysis where we're going to make some assumption about the distribution of both costs and events. So here's an example where the investigators looked at urinary tract infection and estrogen treatment for it. And so these data all came from the literature. So what I mean by this, for those who got the estrogen treatment, 68%, or I guess you could say the cure rate was 68%, where they had no, after that, they had no infection. 32% still had an infection. And then if they still had an infection, they might have a complicated or uncomplicated infection. And then if it's uncomplicated, they might have what was called a susceptible, uncomplicated, or non-susceptible. And so they have percents or rates here for each one that were obtained from the literature. And so this says that if the patient has a urinary tract infection, then about 3.5% have a complicated infection, 96.5% have an uncomplicated, and then if they have a complicated one, we sort of stops there. If it's uncomplicated, then it can go to either susceptible or non-susceptible. And then we have the same thing for those who didn't get estrogen. About 3.5% develop a complicated UTI, and about 90, a little over 96, an uncomplicated one. And then we also have the susceptible and non-susceptible infections here as well. And then so we have a cost for each of these. So for a complicated UTI, it was $6,000, $900, almost $1,000 for a non-susceptible, uncomplicated UTI. And then they had an estimate of quality adjusted life years of 0.73 if an UTI developed, 0.96 if it didn't. And so we can then carry this out. So what we do is a simulation. So I assume, for example, that I have 1,000 patients with a UTI, 1,000 get estrogen and 1,000 get no estrogen. And so then I just carry this through, those numbers through with these rates and the costs, and come up with a incremental cost effectiveness ratio. And in this case, we had 3 different vehicles for application, cream, tablet, and ring. In the previous slide, I saw there was the one for the combined, where risk reduction was 68%. And so then I have the cost per year for those on estrogen therapy, and the cost per year for those not on estrogen, which you can see is going to be the same because they're not getting any of the treatments. The cost difference, and then the ICER is calculated by the difference in cost divided by the difference in the quality adjusted life years. And so you can see that we get different ICERs here None of these are anywhere near the $50,000 mark. But it would depend on in this case, obviously, the treatment for urinary tract infections. So maybe $1,600 to treat one case or to cure one case of UTI. Maybe that's really high. If we had to maybe pick one, it would be the tablet application here, which is actually dominant. That it's the cost difference is it's actually cheaper than no treatment at all, and so it's a dominant strategy. So in this case, I'm not going to go into it here, but what we would do then for sensitivity analyses, we would if I can go back here to the slide, we would vary some of these inputs. So for example, what if this was say 65% instead of 68 or 60%? What would it be? Or if for no estrogen, what if this was 5%, or what if it was 2.5%? So we would vary it that way, and then we would vary the cost. So for example, for a complicated UTI here of $6,000, well, what if it was actually $9,000 or $10,000? Depending on what would be a reasonable range to look at. And that's how we would do sensitivity analyses in Markov modeling. Okay, so as I've mentioned that in doing it, we always do sensitivity analyses when we do a cost effectiveness research, because the costs that we get are subject to error. And what's reported for a cost in one study may be different, maybe quite different from the cost of the same thing in another study. And so what we need to do is demonstrate how the variability in costs as well as treatment effectiveness changes our conclusions. And so what we do is as we saw in the tornado diagrams for the IPE study, that the results for the cost of the drug are not insensitive to variation in the parameter. They were very sensitive to that, whereas some of the others weren't so sensitive. So we can do different types of sensitivity analyses. We can vary one variable at a time, so we can maybe vary the costs. Maybe we can vary the effectiveness. Two-way, obviously, we can maybe vary two at a time, which is obviously going to be costs and effectiveness. Or there's some other variables that we might want to vary as well, and do a multi-way sensitivity analysis. One that's more commonly used is what's called probabilistic sensitivity analysis, and I'm going to give an example of that. And then we'll do what are called scenario analyses. And so this is asking, what if kinds of questions. So in many analyses, we assume that the treatment effect lasts for the length of the study, or we carry it past the study period. But what if the treatment effect only lasts 1 year? How is that going to affect the cost effectiveness? And so we might do different scenario analyses that will show how sensitive our ICER is to variations in the inputs. And so let me just talk a little bit about probabilistic sensitive analysis here, or it's also referred to as a Bayesian sensitivity analysis. Because in this case, for all the parameters, we're going to assume some particular theoretical distribution. Then we're going to simultaneously draw random values from these distributions. And we're going to calculate the ICER with the drawn value. We're going to repeat this process a large number of times. Obviously, we're doing this in simulation. And then we report the mean and the standard deviation of the distribution, or the percentiles of the distribution, or what proportion of the results are below a threshold value for the ICER. And I'll see if I can kind of thought of a way to do this in a, I guess, a cartoon sort of way, but not sure how effective this is. But here's an example of different values for the Courage trial, again, which is a fairly old trial now, but differences in effectiveness and in costs. And so we varied these based on the range, and you see that for each one, we have a assumed distribution. And so this is kind of a schematic here of what we're doing when we do probabilistic sensitivity analyses, is that we're going to take a random draw from our different distributions. So we might, for example, draw from a distribution where the patient had a stroke, they were taken a torvastatin, they had a history of angina, and then we would also have to have in here how long they were followed. But we, from the different distributions, we would take a random draw, and then we would repeat that a large number of times, and then we would calculate the ICER, the difference in cost divided by the difference in qualities over. And for example, if we did 100,000 simulations here, so doing the Bayesian analysis, and again, the difference here, which is, that's what you do when you do Bayesian analysis, you have to make some assumption about the distribution of your data. And so just to give you an example then of how we present this graphically, this is from the Courage trial, where we were looking at PCI, percutaneous coronary intervention, and optimal medical therapy. So we had PCI plus OMT versus OMT alone. And so this is a plot of our cost in our cost effectiveness plane of the simulations. And in this case, we do contour. We did a contour plot where the large dot in the middle is the average ICER that we would calculate, and then the first ring is like the 90th percentile, so 90% of the bootstrap replicates would fall in here. The middle one is the 95th percentile, and the outer band is the 99th percentile. So you can see here, although it's didn't make it really clear in this graph, but here's zero as far as effectiveness, and so you can see that the distribution of our ICERs is pretty much zero. Cost here is the zero cost would be down here. So the treatment of PCI would always be greater than optical medical therapy, but the results aren't necessarily anything other than zero as far as effectiveness is concerned. And I'll just mention this briefly. We also do, as you saw, we had results and where we calculate cost effectiveness beyond the study period, which is usually what is of interest to a lot of people. So what we do is we project beyond the in-trial data. And so in beyond the study period, we need to come up with a time horizon. So are we going 10 years beyond the trial or lifetime? And again, that sort of depends on the population or the sample. So for example, if you are doing a study where most of the patients are elderly, say over 65, doing a lifetime or doing anything beyond, say, 10, 20 years isn't very realistic. Then we also have to estimate life expectancy beyond the trial period, and as well as the probability of events beyond the trial period. And then we also then do discounting, just like we did in the in-trial analysis. So this is doing beyond the study period, obviously gets a little more complicated than, well, a lot more complicated than doing cost effectiveness within the trial period, because you've got to make quite a few assumptions here. And some of those, may or may not be all that accurate. And then finally, when we have multinational trials, like I mentioned, the IPE study was multinational, where you have patients from different countries. And some people have asked, well, why don't you use the cost from the particular country? Well, you can't really do that, otherwise your cost effectiveness, incremental cost effectiveness ratio doesn't apply anywhere. And so it's, when you have multinational trials, like it's pretty easy to get costs of different events from the more wealthy countries here, obviously, where it's more difficult to get those from the not so wealthy countries. So I have a few publications here. I think the reference for the one that I shared on IPE, I think that was at the bottom of one of the slides, if you care to look that up to see how the entire paper looks like for cost analysis. So I want to, again, thank you for your time. If you have any questions, feel free to email me. As I've mentioned before, the slides will be available to all who have registered, as well as the video of the presentation. So again, thank you for your time, and our next presentation will be in May. I forget which day it is now, but the third Friday in May. So again, we will see you then.